Sure. Well, hello, everyone. Lovely to see so many faces for this review session. Just saying just a second ago, the basic plan here is to kind of give you some preparation for the exam. Roughly, my thought was very quickly talk about the structure, what it's going to look like, a friendly reminder again about how your grade for the course is determined, and then just slowly walking through as much of the practice exam as seems pretty feasible. Um, so yeah, that's the kind of plan for the session. Obviously, if there's any kind of other questions you guys have or anything like that, we can do them. I've got my sweet, sweet whiteboard here. It's a blast from the past back doing the COVID teaching. Such a fun time. We were just talking about that. Um, But yeah, so first things about the sort of structure of the exam. So the practice exam is the exact same structure. That is, it has the cover page and the same number and type of questions as will be on the actual final. Notably, if you check out the practice exam, you'll see that it has two sheets with rules on them. So there's the rule sheet with the natural deduction for TFL, and then the natural deduction for our various ML systems. Those will be included in the final exam. So if you remember way back, I was saying you don't have to memorize the rules. This is, yeah, the big reason. You don't have to have the natural deduction rules memorized, but it's important you know how to use them and things like this, because just having the rule sheet in front of you, frankly, isn't really going to help unless you already know how to use them. So that's the place to start. And with regards to the exam, so there's four questions that will be right at the beginning on definitions. You know what the first one's going to be. You were promised, hopefully, way back, the first question on the final and the midterm, the definition of validity. Then there'll be a section where we have proofs, so natural deduction for TFL. Here we have 6 questions. Each proof is worth 2 points apiece. Notably, these aren't necessarily going to be wild and crazily difficult proofs. Notably, too, they're worth 2 points apiece because the idea is that if you get it broadly right, but maybe make a little mistake along the way, we can still find a way to give you, a point or a point and a half or something along those lines. Then we have section C, where you're tasked with giving some counter interpretations for ML. So this is something like what we did, oh God, let's call it 2 weeks ago, where there's a particular modal logic claim, and what you're tasked with doing is generating a little diagram that shows why the claim fails. So we'll go through those in a bit. Then there's 3 questions where you're given ML proofs, natural deduction proofs, and the task is to label all the rules. So input the rules from here. Here again, it's fairly straightforward. Note that we thought about putting some actual exercises here for you to construct your own proofs, but frankly, I just found that those were so difficult that this seems like a kind of a nice compromise. And then the last section, we have 2 essay questions. There'll be 5 points apiece, one from each of the 2 final topics that we talked about. So one on ontological commitment and one on the sort of stuff about identity that we talked through. That's the exam. Not super duper wild and crazy. The whole thing is scheduled for 2 hours, so you'll have plenty of time to work through the natural deduction proofs and to go back over and to answer things like the essay questions. Note that for these essay questions, you don't need to be super long. So we're really looking for something like 200 words, maybe a little less, maybe a little more, depending on how succinct you are or how many examples you want to use. You don't need to have pages and pages to answer these questions. Um, Before we go on, make sense? All clear? Beautiful. Cool. So yeah, that's the kind of big opening bit, the structure of the exam. The next thing I wanted to mention was just again a friendly reminder about how your grade is determined. So the thing to really re-emphasize with your grade here is that we're not interested necessarily in where the points come from. So we're going to take your top 10 homework assignments, so a max of 20 points from homework, your score for the midterm, and your score for this final exam. Add those three together, and this will give us some number out of 100. We'll then take that number, divide it by 10, and that's going to be your grade. And to stress, it doesn't matter how well you do on this one in some sense. All that matters is how many points you get in total. So you could absolutely ace this exam, have gotten like a 10 on the midterm, have done all the homework, and still get a very good grade in the class overall. So again, that's just to kind of remind you about how your grade is determined. Yeah, those are the big things. I guess the next kind of step was just to turn and walk through the practice exam. Um, make sense? Cool. So we can start by talking about exercise A. So this is again the kind of state some definitions. Note here that the definitions we'll be looking at will only be the ones that we've talked about in the second half of the course. So none of the stuff from the beginning. And note that it's only the ones that we've used where they were appeared in like the blue boxes. So this really means it's going to be things like being jointly contrary, being a theorem, being provably equivalent, being a modal tautology, or being modally valid. So there's really only, I want to say, something like 8 or 9 possible definitions. So there's not a ton of them, which is nice. And that's the first thing to start. And of course, you know what the first question is going to be. The first one is going to be the definition of validity. Right? That's always. So that's the first thing to note. Then for exercise B, we have various TFL proofs. So this is stuff we talked about in, let's call it weeks 8 and 9, I think. And what I thought we could do here is go through them together. So I'll switch over, I'll pin the whiteboard real quick. And we can go through these together, right? So I'll kind of talk through them as we go. So for our first one, we've got okay. So that's the proof we want to build. Excuse me. And the thing we can start off with is note that, right, the main operator of our conclusion. That's always a good place to start. So in this case, our main operator is the negation. So that suggests that what we're going to do is do a negation introduction. So we'll, start off writing down our assumptions, drawing our assumption line, dropping our proof line. And then because we're very likely to do negation introduction, our first move in the proof is going to be to assume the thing we want to negate. We're going to assume it, and then the aim is to try and show that if it were true, bad things would happen. So that means what we want now is this subproof needs to end in a contradiction. And I should ask, can you guys see that okay? Is it visible and everything? Perfect. Thanks for being my guinea pigs. Right. So we want this to come to a contradiction, right? And now if we want this to come to a contradiction, what we can do is look to see where is our negation going to come from and where's its unnegated cousin going to come from. And we've got the negation right there. So we can get not S very quickly through conjunction elimination on sentence 1. And now the trick is, how are we going to get S? Well, we've got the antecedent to that conditional right there. So we can get the antecedent through conjunction elimination on 1. And then together with this conditional and the antecedent, we can now run conditional elimination to give us S. And hey, there's our contradiction. So we could do negation elimination on 5 and 3. Right? And now remember, what was the point of our subproof? Our subproof was designed to do negation introduction, and it's done its job. It started with a sentence, and we've shown that if that sentence were true, bad things happen, so we can conclude it must not be true. And there we go. There's our first one. Didn't even take us 2 minutes. I'm going to turn this on, see if that helps with that. Okay. So before we go to the first one, any questions on that? Or to the second one, I should say. Any questions on the first one there? Does that make sense? Beautiful. So the biggest thing to remember is when you're doing these, a good kind of place to start, because as we know, the hardest part is figuring out that first move. The place to start is by looking at your conclusion and thinking about what your last move is very likely to be, because that can then help you figure out how to structure the whole of the proof. So let's go to our second one. Our second one, I'm just going to write down the assumptions, right? So we have, that's a G. So we have that conditional, and we have not E and C. And the conclusion we want to get to is G or Q. So we can again start here by thinking about how we want to kind of go through this proof. And if we look at our conclusion, you can see its main operator is a disjunction. So it's pretty plausible our last step is going to be disjunction introduction. And here's the nice thing, right? Disjunction introduction is easy because all you need for disjunction introduction is one of the disjuncts, and then you can bolt on or whatever you want. Disjunctions are easy. So in this case, we're going to either want to get Q or G. And Q, well, it ain't in there. So our aim is going to be to try and get G. Make sense? Okay. So then we can ask, well, where's G going to come from? And here we can turn and look at our assumptions, and we can see it right there. So now what's in the way to get G? Well, we have that disjunction, and we have the conditional. So we can ask, okay, how can we get rid of the conditional? Well, that would require the conditional and the antecedent. We got the antecedent right there. So that at least gets us down to the disjunction. So we can go ahead and do that. We'll give ourselves C from conjunction elimination on 2. And then we'll use the C we just derived and this conditional to give us from conditional elimination on 1 and 3. But now we're stuck, right? We got to get rid of this disjunction. Now, what can we do? What options do we have to get rid of the disjunction? Well, the most flat-footed one, right, is disjunction elimination. And as we remember, disjunction elimination is the one where you have to do 2 subproofs, one with either disjunct, and they need to get you to the same result. But we have another cheap trick that we can do here. What's the cheap trick we can use to help us out? I'll help you out because there's not so many of us, right? The cheap trick we got is we can do disjunctive syllogism. So disjunctive syllogism says if you have a disjunction and the negation of one of the disjuncts, then you can get what's left. So we can take negation E, we can get it from conjunction elimination, and we can use negation E and this disjunction to give us G through disjunctive syllogism 4 and 5. And again, the idea with this rule is that if you have a disjunction and you know that one of the disjuncts is false, then you can derive whatever's left. So we get G, and that sets us up because remember, this is what we wanted to finish with. So our last step, exactly as expected, is disjunction introduction. So we just bolt on or Q. Cool. And there we go. So again, how did we kind of reason our way to this one? We looked at the conclusion. We realized, okay, it's plausible our last step's going to be disjunction introduction. That means getting at least one of the two disjuncts. We realized we could get G, so we did that. We worked our way to G and then added on the disjunction. Cool. Okay. Questions on that one? We feel good? Make sense? Beautiful. On to number 3. So again, for this one, I'll just go ahead. I'll write the assumptions down. So there's our two assumptions. And we want to derive D. So first thing we can see, given the kind of sentence our conclusion is, right? What kind of rule do we expect we're going to have to use? Well, it can't be any kind of introduction rule, because introduction rules always give us a complex sentence. They always give us a sentence featuring the relevant operator. And since this is an atom, we know it's going to be some kind of elimination rule. So that's the first thing to note. That's helpful. And then we can look to see, is this sentence, this atom, anywhere in our assumptions? Well, yeah, it's right there. So that suggests our last step is going to be biconditional elimination. But of course, to do biconditional elimination and get D, we're going to have to get A. Because biconditional elimination says you use the biconditional and one of the sides to get the other side. So now it becomes the trick of where's A going to come from? And if we look here, we can see it in sentence 1. And in fact, it's in 2 sides of sentence 1. It's over here in this disjunct, and it's over here in this other disjunct. And that already should set off some alarm bells. Because if it's in both sides of this disjunction, it means we can use disjunction elimination to give us A, and then we can use A and our biconditional to give us D. And then it's all over with the shout. So let's do it. Our move is going to be to eliminate this disjunction to get out A, and then use A and the biconditional to get D. So biconditional elimination, mentioned it a second ago, but the idea with this rule is that you have 2 subproofs, one that starts with the left disjunct and one that starts with the right disjunct, but they end up in the exact same place. So we can start with A conjunction B, our left disjunct. And we want this to end in something we can also get to with the other one. So easy option, let's just have it be A. And that will be conjunction elimination on 3. And look at that. This subproof's already done. Already gotten us to somewhere that we want to get to. So we can go ahead, close this subproof, move on to our second one. And our second one needs to start with our other disjunct. So it needs to start with A conjunction C. And this subproof needs to end in the exact same thing. So what's our move at line 6? What rule are we going to use at line 6?
The same as line 4.
Yeah, exactly. We use conjunction elimination. And this time, though, instead of eliminating the conjunction at line 3, we eliminate the conjunction we have at line 5. And now we've shown, hey, no matter which of the two disjuncts you pick, it's going to get you to A. So we can close both subproofs because they've done their job, get us to A, disjunction elimination on 1, and we cite our two subproofs, 3 through 4 and 5 through 6. And now we can use A together with 2 to give us D. And there we go. So that was nice. It's not too hard. Note a kind of neat little thing here. We did it so that we got A using disjunction elimination. But what's another sentence we could have got inside these subproofs? So instead of ending both subproofs on A, we could have used disjunction elimination inside the subproofs, sorry, biconditional elimination inside the subproofs to end both of them with D. And then that would have made our last step the same sentence, but it just would have been through disjunction elimination. So we could have done this operation inside the subproofs had we wanted to. Doesn't matter which way, it's all the same. But do we see the difference? Do we see how we could have done that? Does that make sense? No? Okay. So watch this way, right? So suppose we're at line 4, and instead of closing the subproof, so we still got this, line 3, this is A conjunction B, and then we get A through conjunction elimination on 3. Now at line 5, instead of closing the subproof, we use the A we've derived together with the biconditional inside the subproof to get D through biconditional elimination on what would be line 4 and 2. And then we keep going, right? So our next step in the would be the exact same. Conjunction elimination. This time, of course, right? So if this is 3 and this is 4 and 5, so that'd be line 6. So line 6. And then we'd use A and the biconditional to get D through biconditional elimination 2 and 7. And then finally, note both subproofs now in this alternative version of the proof still end in the same place. But they don't end in A, they end in D. So we could get it through disjunction elimination on 1, and we'd cite 3 through 5 and 6 through 8. So again, it's just a different way to do the same thing. Instead of getting A out via disjunction elimination, we could have used the A's we derived inside the subproofs to get D out via disjunction elimination. Make sense? Perfect. That's what we like to see. And note, there's really no deep dark difference here. This one's just one line longer. Okay, on to number 4. Cool. So we'll slide back up the page here. Let's look at number 4. So number 4, we've got So our one assumption, and we want to prove not x. So our one assumption is a negated conditional, and our conclusion is not x. So let's start by first having a sip of terrible, terrible decaf. I would say it's refreshing, but that'd be a bold-faced lie. So we've got our negation x. That's where we want to go. If we look at negation x, our first thought should be the last rule is probably going to be negation introduction. Right? That's the main operator of the sentence. So we can expect that that's probably the last step in the proof. Now, negation introduction requires a subproof that starts with the sentence we want to negate and ends in a contradiction. We know it because we did it over here. So that means we're going to start a subproof beginning with x, and we want this subproof to end in a contradiction. Now, of course, to end in a contradiction, that means we're going to have a sentence and its negation. So let's look and see. At this point, where are we going to get our negation from? Well, it's right there. So now it becomes a trick of, could we, inside this subproof, generate the unnegated conditional? And we absolutely can. So here's a really cool little two-step, okay? If you have a sentence, you can quickly generate a conditional with that same sentence as the consequent. You do it this way. Inside our subproof, we're going to open a sub-subproof. And this sub-subproof is intended to do conditional introduction. So we're going to assume Z. We're now going to use a ridiculous rule, but it's a rule we have, reiteration. Right? So this is the one that lets us repeat ourselves. So we repeat ourselves. And now this sub-subproof has done its job. Because what can we now step out and do? What rule can we use at line 5? Well, we can do conditional introduction. And we can get because conditional introduction says, hey, if this additional assumption were true, then you could get to this. But we already had x. So yeah, no wonder you could get to x because we already knew it was true. So this little two-step is something you can always do. If you have a sentence, then you can build a conditional with that sentence as your consequent. And now here's the neat thing. The sentence we've just built, that conditional, directly contradicts our opening assumption. So we can very quickly get a contradiction through negation elimination on 1 and 5. And now why did we want that contradiction? What was this designed to do, the subproof? Well, remember, our subproof was designed to get us to do negation introduction. So we can now close our subproof because it's done its job. It's shown us that if x were true, bad things happen. So x must not be true. And we do negation introduction, and you cite the subproof 2 through 6. Beautiful. Okay. Now, before we go on,
Wait,
again,
I'm sorry, I have a question.
please, yeah.
In line 2, why do we have an X?
Good. So what we're aiming to do, right, is also nice to see you. Sorry, I didn't notice you were here.
Oh yeah, sorry.
No, it's okay. It's good. So what we're aiming, right? That's our conclusion. We want to get to negation X. So the aim to do it is to get negation introduction. So that means we take this sentence we want to eventually negate and show that were it true, it leads to a problem. So we started with X because what we're trying to do is to show that if X were true, it would lead to a contradiction. So it must be false. Does that make sense?
Oh, yes. Okay. So it doesn't have to be one of the premises
No,
necessarily.
no, not at all. And in fact, in this case, right, it's the kind of opposite of the conclusion we wanted. So the thought process was, since the conclusion starts with a negation, let's think about doing negation introduction, and that was the motivation for doing this. Cool?
Okay, thanks.
No problem. It's a good question. All right. Shall we move on to number 5, or are there more questions on this one? Good. Okay. So let's try number 5. So number 5 is a very silly one. This is me trying to have my fun where I can, you know? So we've got one assumption, and it's just P. And what we're aiming at is that's what we want to get to. So we have, I think there's an extra. Ignore that little bracket there. So what we want to get to is this biconditional. And our assumption is P. So the first thing to note here is that our assumption and our eventual conclusion, not much connected there. Right? This has got A's and B's as its parts, and P is not really one of those. That's the first thing to note. Second thing to note is, again, if this is going to be our conclusion, what rule do we expect is going to be our last step? Well, here again, right, we can look and see, right, the main operator for this sentence is the biconditional. So plausibly, our last step is going to be biconditional introduction. Because that's going to guarantee to give us a sentence that looks like this, that has a biconditional as its main operator. Biconditional introduction requires that we have one subproof that starts with the left and ends with the right, and then a second subproof that starts with the right and ends with the left. So let's go ahead and kick open our first subproof, and we'll get to thinking about it, right? So we want to start with the left-hand side and end with the right. And this subproof needs to somehow end in that sentence right there. Interesting. Now, what's weird about sentence 2? If we look at sentence 2, the left-hand side of our biconditional, well, it's basically a contradiction, right? Because it says A is true and also A is false. So this should set off an alarm bell, right? What's the rule that's going to get us from this to that side? It's a beautiful rule. It's my favorite rule. It is explosion. Explosion says if you have a contradiction, you can then get anything at all. So our plan for this subproof is to get a contradiction, use explosion, and then derive that side. And it'll be easy. So we'll take sentence 2, and we get both parts, both conjuncts. And now we've got a sentence and its negation, so we can immediately use negation elimination to give us our contradiction. We've set the bomb up. Now we blow the bomb up. We can use explosion to now give us any sentence at all. But of course, the sentence we want is that one. So if I write it correctly, through explosion on 5. So there we go. That's given us our left to right conditional. Now we need to figure out how to do the right to left. So we close this subproof. We move on to our next one. And this is going to start with the right-hand side and get us to the left. Okay. So we know where this one needs to end. This subproof needs to end back at that sentence right there. And that looks weird because, again, if we look at what we've got, it doesn't have any A's in it. So it's really unclear how we're going to get A conjunction not A. But this sentence also has a very particular structure. And if you see a negated disjunction, that should set off alarm bells. That should suggest a rule. And the rule it should suggest are the De Morgan rules. So the De Morgan rules say if you have a negated disjunction, you can convert it to a conjunction of two negations. That is, you take this or, you turn it upside down, and you slap negations in front of both sides. So if we De Morgan number 7, we get not B, and not B. And a thing to note here, remember, is that you're going to have the rule sheet in front of you. So when you're going through and you're looking at these sorts of things, remember, oh, hey, this is a structure that the De Morgan rules can apply to. If I use the De Morgan rule, what's it going to let me do? What's it going to give me? How could I get something out of this? Because if we use the De Morgan rule here, we see this sentence, oh, it's money. Because from this sentence, we're going to get a contradiction. And we'll use explosion again. So we're going to take the conjunction. We're going to break both parts off. Conjunction elimination on 8. And now we have a sentence and its negation. So we can use negation elimination to get us a contradiction. And now, having set up the bomb, we blow it up again. And that will give us whatever we want, right? We can use explosion to give us whatever we want. But of course, what sentence do we actually want? Well, we want A conjunction not A. And now look, we've got one that gives us the left to right direction, and a second subproof that gives us the right to left, so we can do our biconditional introduction. We can get A conjunction not A, if and only if, not B, or B. Nice. And that's biconditional introduction. And we cite the two subproofs, 2 through 6, and 7 through 12. And just like that, right, we've got our proof. Easy peasy. So, again, how did we work this one out? We looked at the structure of our conclusion. We noted that the parts here just didn't really have anything to do with the assumption. So what we did was we figured out how to do, in this case, biconditional introduction to give us the sentence we wanted. And that meant one subproof with the left to the right, and the second subproof with the right to the left. And they both had basically the same structure of building contradictions. Sorry, George, go ahead.
How can you say then that this is derived from the assumption of P?
Nice, nice. So in some sense, P was unnecessary. Right? It is still true that we've assumed P, we just didn't really need it.
Okay.
So in fact, if we're really taking it seriously for a second, we could have just proved that. So we could have just proved that from nothing at all. And if that's the
Yeah.
case, what would this have been? Do you remember what we call those kinds of sentences? The ones that we can prove from nothing?
What was it called again?
Is it a
I f-
theorem?
Yeah, you got it.
No.
It's a theorem. It's a theorem, right? So a theorem is a sentence that we can prove from nothing at all. And in fact, if we look at number 6, that's exactly what it is. Number 6 is asking us to prove a theorem. So this was a kind of warm-up exercise to remind us about what theorem proving looks like. We had a premise or an assumption. We didn't really need it. But I thought it'd be rude to just throw you right in the deep water right off the bat.
But this is a theorem because it's one big contradiction fest.
In a sense, right? The reason why this biconditional's always true is because both sides are always false. That's
Yeah.
exactly why, right? Both sides are basically contradictions. Nice. Cool. On to the next one. Okay, so let's go to number 6. I'm going to flip it over, give myself a little more room. My high-tech whiteboard. I got to get me one of them iPads like Michael has, but, I just find this so much more easy. So, our last one here is, as I said, proving a theorem. So we're going to prove that this hideous sentence, which I'm going to write down first, is a theorem. So we have that as our antecedent. And our consequent. So we're going to prove that this conditional is true. Okay. Now let's think about it for a second. If we're going to prove that this conditional is true from no assumptions whatsoever, our rule, given the main operator here, is very likely to be conditional introduction. That is, we're going to assume that, and then we're going to try and close our subproof with this. Make sense? So, proven theorems, that means starting from no assumption. So our first numbered sentence is below the assumption line. Given the main operator of our conclusion, we can expect that the main rule is going to be conditional introduction. And that means starting a subproof, beginning with our antecedent, and this subproof needs to end in the consequent. With me so far? Make sense? Okay. So now let's think. We want this subproof to end. Ooh, probably helps if I could count. We want this subproof to end in our consequent. And if we look at our consequent, what's the main operator of the consequent? Well, it's the negation. Because it's this negation's got the scope for the whole thing. So that means it's very likely that the move inside our subproof that's going to give us this is going to be negation introduction. Because again, if that's the main operator, we should think about a rule that's going to give us that operator. Okay, cool. So that means we're going to do a subproof that starts with the sentence we want to negate. We want the subproof that starts with the sentence we want to negate, and we want this sub-subproof to end in a contradiction. Right? And now why? Because again, the idea is that we want the subproof, we're starting at 1. That subproof needs to end in this sentence. And the best way to get this sentence is to use negation introduction. And that requires a subproof that starts with the unnegated sentence and ends in a contradiction. So that's why we've opened this subproof at 2. Okay. Now, how are we going to get our contradiction inside our subproof? Well, here's the trick. We look and see, where's our negation going to come from? And can we build the unnegated twin? And if we look, it's pretty easy. Our negation is going to come from 1. So we're going to build this biconditional. And we have our tools right here. So our first move is going to be conjunction elimination. Let me write it correctly. Conjunction elimination on 2 to give us both of these conditionals. Now, we're going to do something that looks really stupid. But we're going to introduce this biconditional. And we're going to introduce this biconditional because, again, we want to generate a contradiction in this subproof that started at 2, the subproof. So we go, okay, 3 deep, assume an A, and we use A and this conditional to give us B through conditional elimination, 3 and 5. And now because we're doing biconditional introduction, we got to do it again from the other way. So we assume B, and we use that conditional and B to give us A through conditional elimination on 4 and 7. And hey, look, now we can do with these 2 subproofs biconditional introduction, 5 through 6, 7 through 8. We've got our biconditional, which contradicts 1. So we can do our negation elimination, 1 and 9. And now we're just going to start working backwards. So we have a subproof that starts with this sentence and ends in a contradiction. So we can now go 1 line to the left and negate the sentence we opened our subproof with. That's negation introduction, 2 through 10. And now our subproof starts with what we wanted as our antecedent and ends with what we wanted as our consequent. So we close it. We move 1 line to the left, which conveniently is our main proof line. And we can do conditional introduction. Take our would-be antecedent and our would-be consequent. And that's conditional introduction, 1 through 11. And hey, there we go. Zoom in a little bit so you can actually read my terrible handwriting. So what was the idea, again, to walk through it? Well, we saw that this sentence was a conditional. So that suggested that our final rule was going to be conditional introduction, which means a subproof that starts with our antecedent, ends with our consequent. And then it just became a process of figuring out how to get the consequent. And the consequent, since it had a negation as its main operator, we figured, oh, it's going to be negation introduction, which is exactly what we did. So there we go. Working it through steadily along. and helping us figure it out. Now, the nice thing here is, again, if you want to think about it generally, the ways forward, you can ask yourself, what's your last move likely to be? What's the last rule you're likely to invoke? And then use that to help you figure out how to structure the proof. So we thought last move's going to be conditional introduction. That means this subproof. Okay, and then it was just sort of inside that subproof, what do I need to do to get me from my antecedent to my consequent? Cool. Okay. And note, just like with all the other ones, this one wasn't a super long proof, right? This one was maybe 12, well, not maybe, I'm looking at it. This was 12 lines. None of these proofs I'm going to ask you to do are going to be really insane, at least in terms of length. And they're not super duper duper crazily hard. Again, if we can start to see what the rules to use are going to be, then it's just a process of sort of stacking them up and figuring them out. Okay. Now, before we move on to the other exercises, going to want to take a second, ask any questions on these ones from exercise C, this sort of, or exercise B, rather, of doing the natural deduction proofs. We feel kind of okay about it. I'll take that as a yes. So yeah, that's the
I
kind of
have
thing.
one question.
Please, please, please.
How do you get points if you get it partially correct?
Good question. So what I'm really kind of looking for is if you have the basic structure of the proof down,
Mm-hmm.
but make a few mistakes. So like, say, if you've done this one and just sort of assumed the biconditional introduction, didn't do the steps, you could still get like 1.5 points. If, say, for example, a similar thing, if, you use the right rules but do the wrong citations, that's going to be a 1.5 out of 2.
Okay.
If, for example, it's not really quite along the right lines, but you're making a couple good moves and starting that way, that can be anywhere from like 0.5 to 1 point, depending on how many rules were used correctly and things like that.
Okay, good to know.
Yeah, no worries. It's a good question.
Thanks. I'm leaving because I have to work.
No worries. Good luck.
Thank you. Bye.
Bye.
I have one question about the last one because it's so many negations. So we assumed that the negation of the biconditional A and B, that is true.
Yeah.
Then what we come up at the end, the negation of the consequent
Yep.
of the final part, that still means it's true, right?
Yes. So importantly, what it means is that the negation is true, right?
Yeah, exactly.
Yeah.
So
Yeah.
1 is true, 11 is true, and that's why the conditional is a theorem. Okay.
Exactly. Exactly. So we're saying, hey, if 1 is true, that is, if this negation's true, then this negated sentence is also going to be true, which is,
Yeah.
what our theorem conditional says in the end. Perfect.
Okay. Thank you.
Good question. Okay. So moving a little slow, but let's go ahead. We'll dive quickly into exercise C. So exercise C is generating counter interpretations. So the idea here, this was the sort of stuff we did a couple weeks ago, where we're given various modal logic claims, semantic claims, and the task is to generate a world picture that shows the claim is false. So we have our first one, where we have that diamond A entails A in S5. And to show that this is false, what we're going to need is a model that makes the left-hand side of this double turnstile true, but the right-hand side false. That is, a model with a world where this is true at the world, but A is false. And if we remember, right, diamond A is true at a world if it can see some world where A is true, and A is true if it is the case at that given world. So our first example here, so this is C1, we could do an instance like this. So we've got a world with A and a world with not A. We'll call this one world 1, and that's world 2. And because it's S5, they have to be able to see each other or see themselves. And if view goes out, it also comes back in. But if we look here at world 2, diamond A is true because it can see a world where A, but A is false because at that world, not A is true. So this is a quick and easy model to show that, hey, the fact that diamond A is true in a world doesn't mean that A is in fact true. Something can be possible without it actually being true. Okay.
Okay, so you don't need to state that it's the case in world 2. It's just generally possible that this is the case.
Exactly. Exactly. So if you give me something like this in the exam, 2 points. Right? So, and let's go to C2. C2, we have diamond R and diamond S in K. Entails diamond R and S. Now, the thing to remember about our various modal systems, and this is something that's also useful to see back in our rule sheet, is our various different modal logics. K is the simplest one. There's no restrictions on the accessibility relation. T, the next one, requires every world can see itself. S4, every world can see itself, and the relation is transitive. And finally, in S5, accessibility is reflexive. Every world can see itself. It's transitive, and it's symmetric. So if it goes out, it comes back. So K, we don't have to have any restrictions at all. We're again going to try and show that the sentence on the left can be true in a world, while the sentence on the right can be false at that same world. So this one's pretty easy. We can just go, okay, let's make it a bigger picture. We can have one world where not R and not S, and it sees a world with not R and S, and it sees a world with not S and R. And we can have that one be 1, and that's 2, and that's 3. So now if we look at world 1, this claim is true. Possibly R and possibly S are true in 1. But it's not the case that diamond R conjunction S is true, because every world it can see, that conjunction's false. So, easy peasy. On to 3. For sentence 3, we have box P, and this is in T, so that means all the worlds can see themselves, to box P. So every world can see itself, that's the restriction, and we want to show that, hey, box P being true in a world doesn't mean that box P. And if we remember, box P means that it will be true if every world it can see is a world where P is the case. And similarly, box P would be true if every world that can be seen is a world where every world it sees is P. So we can think about it this way. We've got world 1. It sees itself, and it's going to see world 2, which of course sees itself, but notably, it also sees world 3, where not P is the case. So in this case, if we look at world 1, every world it can see is a world where P. So, cool. But is every world a world it can see a world that only sees P worlds? Well, no, because while 1 can only see P worlds, 2 can see P and not P worlds. So while box P is true at 1, box P fails. And it fails because it is true at world 2.
Okay, I have a question.
Please.
But stating that box P needs to be true, doesn't it like wait, it's not true because there is a negation P, right, in world 3.
But
Doesn't that
note that 1 cannot see 3. Right?
so it doesn't matter that it negates P?
Doesn't matter because 1 cannot see it, right? Think about it this way. If relations here just are like what you can physically touch, right? It might be such that everyone 1 can touch is a P, but not everybody that 2 can touch is a P, because it can touch itself and it can touch a non-P. But 1, its arm ain't that long. It can't reach that far.
Okay. So do you always have to like view it from 1 to 3? For example, you can't start in box 3.
You totally could. I mean, but note that remember what we're trying to do is to come up with cases that show why this entailment fails. So all we're really interested in is there even a single world that makes the left-hand side of this true and the right-hand side of this false? So, if 3 did the job, that'd work too. But in this case, 1 is the one that's helping us because it's where we can get box P, but the double boxed one fails. So that's the only reason here, right?
Okay. Yes. Thanks.
No worries. George, did you have a question too? I saw the mic go. Yeah.
Yeah, for the second one, why do
Yeah.
you need the first world with the two negations? If
This could be the case, right? It could just be R and S. That would work as well.
no, I mean, could you do it with two worlds?
Absolutely. Yeah. So you could just do it this way. So we'll have not R and S in world 1 and R not S in world 2. 1 can see itself and can see 2. So in this case, that would mean that in world 1, diamond S is true because it can see itself. And diamond R is true because it can see world 2. But the conjunction is never possible because there's no world that 1 can see where the conjunction's true. That would also be perfectly fine.
Okay.
Cool.
Yeah.
Perfect. All right. Last one. So we do number 4. So
Is that
C4.
is that S4 also or
This one's S5.
okay, so just for my memory,
Yeah.
which one was transitive again?
Good. So K, nothing. There's no
Yeah.
restrictions. T, it's reflexive. S4 is reflexive and transitive.
Okay.
And then S5 is reflexive, transitive, and symmetric.
Yeah.
So it's the one that's got all the restrictions in.
Okay. Okay, good.
No problem. Okay. So our last one here, we've got box T, box not F. Okay. So in this one, we've got the S5 restriction. So that means, right, again, it's reflexive, symmetric, transitive. And we've got 2 sentences that need to be true. T, box T, and box not F. But we also need it such that diamond T conjunction not F is false. Very weird. So let's think about it, right? We know that in order for box T and box not F to be true, every world that can be seen needs to be a T world and a not F world. Okay? But similarly, if every world needs to be that way, then it seems very weird that we could also still get it to be such that there is no world where T and not F is the case. So how might we do this one? This one's hard.
Doesn't
Go ahead.
doesn't the entailment suggest that it is not the case in one particular world?
Nice. Well, so I mean the entailment, so if this tells us, right, every world that can be seen as a T, every world that can be seen as a not F. The consequence says there's at least one world that's a T and a not F world. So we have to somehow get it to be such that effectively, in order to show that this is false, we need that to be true. We need it not to be the case that there's even a single world that's both T and not F.
Yeah, but a single world where that's the case within itself, right?
Kind of, yeah. So there's not even a single visible world where this is true.
No, I mean, maybe because it's S5 and they can all see each other. So T and not F means that it could also be possible that T is possible in one world and not F in the other, and then it's still a conjunction? Or does this still means that it needs to be not true within its own world?
Ah, good. Yeah. So importantly, I see where you're after here, right? Thinking about just the like, how do we get this to come out false? But remember that this bit over here requires that every world or every accessible world is both a T and a not F world. So our first bit here is actually pretty heinous. It's requiring something pretty significant. So this is kind of a dirty trick. But if we think about it, right? The bit over here, this requires that there's at least one world that can be seen, T and not F. But remember what we said here. Do we remember about the silly restrictions? So if we think about how necessities work, right, you can get necessities to come out true simply on the cheap. And you can get necessities to come out true on the cheap by having it such that basically no worlds satisfy it. If you don't see anything. So one way you could get this to work in a very silly way, right? And it doesn't quite work if it's S5. This should be, it needs to be something weaker like K, is we could get a world that's like this. So a world that's like this, where it doesn't even matter what we fill in, as long as it sees nothing, would make these two true and that false. So this is a kind of weird one where effectively what the question's trying to force us to do is to think up a situation where we have a world that simply doesn't access anything.
And what if you had two worlds, one with T and one with not F, but they can only see themselves and they see nothing else, because then it's still, is it
Nice.
still transitive and
Nice.
symmetrical enough?
Cool. So note in this case, right? Is box T true here? Yeah. Is box not F true here? Yeah. Is box not F true at our T world?
No.
Well, yeah, it is. Because every world it can see, well, it kind of misfires. So there's a way when we can read this as like, yeah, sure, it's true, because it's vacuously true. The world is gappy, so we'll read it as a not F world.
But then the second world still needs a T, but then that would.
Yeah, we'd end up in a very weird situation. So there's something weird about this. I think we've made a mistake when we wrote this one. But this is easy if we think about it in terms of K. Because if we make this instead of S5 in terms of K, you can get a world that makes this true and this false by simply having it not access anything. I wouldn't stress. I think this one's a typo. My suspicion is that we should not have had S5 at the bottom there, but that's fine. It happens. It's also a good excuse because it's worth mentioning if there are typos in the actual exam, so questions like this one that aren't possible, then you get the points for free because that's a mistake on our part. So that's a handy thing. But good. Okay. How are we doing? Oh man, already out of time. Okay. So I want to quickly talk through exercise D. Um, Here it's probably helpful to briefly just share my screen for a second. Okay. So in this case, with these exercises, note that what I've done is I've just taken some of the ones that we did in the practice, from the modal logic primer, taken the proof out, and I've removed the rules. All you have to do is go through and label the steps that have rules or that used rules with the appropriate one. So for our first one, for example, right, you're trying to show this in K. So we have, right, our opening assumption. Our first line with an actual rule is line 4 with double negation elimination. And then 5 will be conditional introduction. 6 is our first ML rule, necessitation. Then 8 is modal ponens using line 6 and line 7 to get us the boxed consequent. Negation elimination. That'll give us then negation introduction, and then finally the definition of possibility to get us this one. So again, it's fairly straightforward here. What I'm asking you to do, you can use the rule sheets that have both the TFL natural deduction rules and the ML deduction rules to figure out how to fill these in. And
The rule sheets will be added to the exam automatically, right?
they are going to be in there. Yep.
Okay, I don't have to bring my own.
No. Please don't, because they'll take it away from you.
Okay.
But yeah, so this structure, like as I've got it's useful to see it here. This structure for the practice exam is identical to the structure you should get for the actual final. So this cover page, then you'll have this TFL rule sheet, this modal logic rule sheet, which again gives you all the basic rules as well as the kind of specific for T for S4 and S5. And then you're off and running. And note here, these are also worth 2 points apiece. So the idea is if you get most of them right, you get like 1 or 1.5 points. If you just get, 1 or 2 kind of rules right, 0.5, you get the idea. Any questions on exercise D? I hope that's reasonably straightforward. Make sense?
Makes sense.
Perfect. So let me go ahead and, we can just quickly talk through E and E here.
Yeah, I had one question about E, and that's the second question. It says the Lumpel Goliath argument, but what I read for that lecture was just the dialogue from Black.
Yes.
It
So
said nothing about a different. What was it? There were no other files that we were supposed to read.
No. So, but this was something we covered in the lecture.
Okay, yeah,
So we
I
talked
wasn't
about the Lumpel-Goliath argument in the lecture. Yeah. So you can go back and watch the video there. But effectively, the Lumpel-Goliath argument is that you have. So you imagine, I'm going to stop sharing because it will be a little bit easier, and I will unpin my whiteboard. So the rough and ready idea here is that imagine you have a lump of clay that a lump of clay and a statue that perfectly coincide for their whole existence. So they kind of come into being at the same moment. The lump of clay is of the exact size shape that the statue is. I kind of maybe carve Lumpel out of a bigger lump of clay exactly in the statue's shape that I wanted it to be. And then, they're around for a while and I get sick of my sculpture because I'm a terrible sculptor and I incinerate them at the same time. So if they perfectly coincided for their whole life, there's a natural inclination to say that they are identical. That Lumpel, the lump of clay, and Goliath, the statue, are in fact actually identical. But they're not necessarily identical because, they might have come into being at the exact same moment. But Lumpel can survive being squashed, where the statue, Goliath, can't. So if instead of incinerating them, I had accidentally dropped them, then it seems like Lumpel survives, but statue doesn't. And this looks like a prima facie argument for the idea that identities are contingent. It might be actually the case that they're identical, but it's possible they're distinct. Does that make sense?
Yeah.
So that's the kind of argument. And there's basically two ways to sort of respond. You can either deny the initial identity and say there was always two things there, or you can just accept that identity is contingent, but then have to explain why you can seemingly have this contingent identity. It looks like numerical identity, being the exact same thing, should be something that's necessarily true, not just merely contingent. So that's the rough and ready argument. Again, we talked a little bit more about it in the lecture. So if you look at like the second half of that lecture, it might give you the stuff there. Cool?
Yeah. Thank you.
Perfect. No worries, man. So yeah, with regards to these questions, maybe just some general things. I'm going to have one question that's on the kind of ontological commitment stuff, and one question that will be on the identity lecture. In both cases, roughly looking for something like 200 words, give or take. The important things are just to answer the questions that are asked and try and answer all of the points of the question that are asked. So for example, like E1, we have define the notion of an ontological cheater, then using an example, show how Quine's three-step method for determining commitment could help us catch said cheaters. If you just sort of say, here's Quine's three-step method, you don't give an example, and you don't define what being a cheater is, you're going to get like 2 points at best. It's very important to try and address all aspects of the question when answering these. But also, you don't need to write me pages and pages. It's just kind of focused, short answers that are directed at the kind of key concepts from these lectures. Yeah, that's the stuff I really wanted to go over. I hope that was reasonably useful and kind of helpful in preparing. What I'm going to do is I'll upload some sample answers for these questions. I've already got a bunch of them here. So I'll write up some sample answers for the other parts, like the definitions, exercise D and exercise E. I'll upload those in the next day or so, but certainly well before next Wednesday. If you guys have any questions in preparation for the exam, please feel free to email or message me on Canvas. And the last thing I just wanted to say is, yeah, I hope that this was a pleasant course, that you guys learned some stuff, had a nice time, and I look forward to running into you guys all again soon.
Thank you so much. I really enjoyed it. Have a
Ah,
nice
no
day.
worries. Thanks for coming.
Yeah, thank you.
Yeah, no worries. So I'm gonna stop recording.